Hey everyone, welcome back to my Calculus 1 series. In today's lesson, we're going to go over curve sketching. So there are a number of steps to curve sketching, but essentially we're going to be putting together everything that we've learned about functions like domain and range, intercepts, asymptotes, symmetry, and then as well as the new stuff that we learned about derivatives. So intervals of increase and decrease, local min and maxes, points of inflection, and concavity from the second derivatives. So there's a whole procedure to basically sketch a curve, and I'm going to be writing down the steps, and then we're going to talk about them, and then we're going to work through an example. So here they are. I've written out 8 total steps, and we're going to go through each of the steps. So firstly, we're going to find the domain of the function, and we can do so by checking if the function is continuous at certain points. And as we'll see in the example, there are times when the function has a limited domain. So we have a function like square root sine, or maybe we have a like 1 over x function, then we'll have some sort of like asymptotes or something. But yeah, we're first going to start off by checking the domain. Next, we're going to check the x and y intercepts of the function, and we can do so by setting the y equal to 0 and then the x equal to 0. So checking where the function intersects the x-axis and where it intersects the y-axis. Next, we're going to check for symmetry, and although this is a rare case, sometimes it's pretty obvious when they are symmetrical. So if it satisfies this condition right here or this condition right here, then we have a symmetrical function. I'm going to link a video I made about symmetry, and it goes a little more in depth as to how we can find if a function is symmetrical. But for this video, we're going to check if the functions are symmetrical or not, and then that will tell us a little bit more about it. Next, we will go on to calculate asymptotes. So as we've learned, we can calculate the horizontal asymptote by finding the limit as x approaches infinity or negative infinity of a function. And if that approaches a certain value, then we say that it is a horizontal asymptote. Again, I'm going to link a video about horizontal asymptotes at the top right now. And vertical asymptotes are kind of the same concept, except we're going to find it not at infinity, but at a certain a value, and as it approaches from the right or the left of that value. And then we check if it approaches infinity or not. If it approaches infinity, negative or positive infinity, then we say that that value of a is a vertical asymptote. So for the 5th step, we're going to compute the intervals of increase and decrease, and we know we can do that by computing f prime of x and finding the intervals. Again, I'm going to link a video at the top right as to how we can do this. And from that, the derivative of the function right here, we can also compute the maxes and mins of the function. So once we have the first derivative and we figured the intervals of increase and decrease and the maxes or mins, we want to take the second derivative of that function to compute concavity and any points of inflection. And we can do that again by computing the second derivative, setting it equal to 0, and then finding the intervals from there. Lastly, once we have all this information, we're going to move on to step 8 and sketch the curve by first drawing out these 7 things that we found out about the function and kind of connecting the dots from there. We'll see how we do that once we go through the example. So let's start off with curve sketching. The first part of curve sketching asks us to find the domain of the function. And just by looking at it, we can see that this is a rational function because it has a numerator and a denominator. And in that case, we are likely to have a asymptote if this bottom were to ever equal to 0, because we would get a division by 0, or if this, like the denominator of this function, were to equal to 0. So let's start off by finding when this function is equal to 0. And it's pretty obvious if we set the root of x plus 1 equal to 0, it's pretty obvious that we can just take the square root of this side, take the square root of this side, we'll be left with x plus 1 equals 0, and that x has to equal to minus 1 for us to get 0. However, there is a catch, and it is that the square root function is only defined like to the right of itself. So if we were to find this root, the function is defined for every value that is greater than minus 1, meaning we can't have a negative within this square root. So if we were to take something like x equals minus 2, this value is actually like it's not in the domain of the square root function because we were going to get the square root of minus 1, and that's an imaginary number. So the square root is limited to all values that are greater than this like root right here. So the domain for this function would be that x belongs to all real numbers such that x is greater than -1. And again, it's not including -1 because we can't include it, because if we do include it, then we're going to get the square root of 0, which is 0, and then we're going to get a division by 0 error. So now for the second part, we are asked to compute the x and y intercepts by setting y equal to 0 or x equal to 0. So let's go ahead and do that. First, let's set x equal to 0. And we can see that we're going to get 0 squared over the square root of 0 plus 1, right? And this is going to equal to 0 over 1, which is going to equal to 0. And so this, when x is equal to 0, right, x equals 0, then y equals 0 too. So the point that we're going to get is 0, 0. Now, if we've set x equal to 0 already. Now, if we set y equal to 0, we're going to get that 0 is equal to x squared over the square root of x plus 1. Now, if we cross multiply this upward, we're going to get that 0 is equal to x squared, and again, x equals 0. So we can see that in both cases, when y was equal to 0, we got x equals 0, and when x was equal to 0, we got y equals 0. So in both cases, we're ended up with the same point, 0, 0. So there is our x and y intercept. Now for the third step, we are asked to compute the symmetry of a function. So let's go ahead and do that real quick. First, we're going to start off by taking f of minus x. And if we look back at our function, if we plug in, the function's right here by the way, if we plug in minus x, what we're going to get is we're going to get minus x squared over the square root of minus x plus 1. And this right here is not equal to f of x. So we can say that it's not an even function. Now, if we were to do the same and plug in f of minus x, again, we were to get minus x squared over the square root of minus x plus 1. And this right here is also not equal to minus f of x, meaning it's not an odd function either. So no symmetry exists because neither of these conditions are matched. The fourth step, we're asked to compute asymptotes. And we can do that by finding the limits at infinity and finding the limits at certain values. So let's go ahead and do that right now. So first, I'm going to take the limit as x approaches infinity of x squared over the square root of x plus 1. So for this limit, we can see that we have a square root in the bottom, in the denominator of the function, which is suggesting to us that we're going to need to rationalize. So let's go ahead and do that. So there we go. We have rationalized the function and we're left with a simpler function. Now we want to get stuff into the c over x form. So we can do that by factoring out the highest power, and in this case it's x. So I'm going to go ahead and factor out x from both the numerator and the denominator. So there we go, and now we can cross these factors out and we're going to be left with the limit as x approaches infinity of x times the square root of x plus 1 over 1 plus 1 over x. And now we can plug in x is equal to infinity, and we're going to get something like this: infinity times the square root infinity plus 1 over 1 plus 0, because this is going to evaluate to 0. So this limit is equal to infinity. Now for this case, we don't need to check the limit as x approaches negative infinity, because we are going to have an asymptote, as we'll see later. Essentially, we won't be able to hit negative infinity because we kind of see from the domain that it's limited from -1 onwards. So our function is kind of going to start at -1 right here, and we're not going to have any values going this way. So this is our limit at infinity. However, we're still yet to compute the asymptote, or the limit at the asymptote. So the limit as x approaches -1 from the right. Note that we have to approach this value from the right because, like I said, we're going to have an asymptote somewhere here because we know that from the domain of the function, and we know that values on this side don't exist. So therefore, we can't approach this asymptote from the left in any way because there are no values there. So we are forced to approach it from the right in some way, which we'll figure out right now. We take the limit as x approaches -1 from the right of this function right here. And now I'm going to break this limit up so that we could solve it. We're going to say that this is the limit as x approaches minus 1 from the right of x squared times the limit as x approaches minus 1 from the right of 1 over the square root of x plus 1. So this limit right here is going to evaluate to just 1 because, I mean, if we plug in minus 1 into here, we're just going to get 1. So this is continuous. This function is continuous, so we can just plug in minus 1 into it and get the limit. So this is going to equal to 1 times the limit as x approaches minus 1 from the right of 1 over the square root of x plus 1. Now to evaluate this limit right here, we can also just plug this value in, and we'll see that we're going to get a 0 on the bottom, and then 1 over 0 is just going to equal to infinity. So we're going to end up getting 1 times infinity, which is equal to infinity. So now we know that as we approach x from the right side, we are going to go towards infinity, like something like that. So now that we've computed the asymptotes, both the asymptote at infinity, like the horizontal one, and the vertical one, it's time to move on to the fifth step. And the fifth step tells us to find intervals of increase and decrease, and we can do so by computing f prime of x and finding the intervals. So let's compute f prime of x. If you remember, f of x was equal to x squared over the square root of x plus 1. And to find this, to find f prime of x, we're going to take the derivative of this. So let's go ahead and do this by using the quotient rule. If you don't remember the quotient rule, I'm going to add a card at the top right now. So the quotient rule says that first we're going to take the derivative of the top, the numerator, and multiply it by the denominator. Then we're going to subtract the derivative of the denominator, which is going to be 1/2 x plus 1 to the negative half. And then this is chain rule, so we're going to multiply by the derivative of the inner function, but it's just going to equal to 1, so I'm not going to multiply it by anything. And then let's not forget to multiply this by the numerator. And like usual in quotient rule, we need to square the bottom. So we're going to get the square root of x plus 1 squared. So now let's go on to simplify this. So there we go. Now that we've simplified this, I'm going to make the numerator have a common denominator. And now I'm going to simplify this fraction even further by dropping this right here down to the denominator. There we go. Now I'm going to simplify this even further. And lastly, we're going to continue to simplify this. So there we go. We've computed the first derivative of the function. And as we know, to find intervals of increase and decrease, we need to find where the zeros of this function are. So we can do that by setting the derivative equal to 0. Now we can cross multiply this upwards, and we're going to be left with 0 equals to x times 3x plus 4. From here, the zeros are pretty evident. We can see that one of the zeros is that x equals 0, and the other 0 would be that 0 equals to 3x plus 4. Bring this over, we're going to get 4 minus 4 is equal to 3x. Divide this by 3, divide this by 3, and x would equal to minus 4 over 3. However, this right here is not in the domain of the function, so we are not going to deal with this 0. Now that we've computed where x is equal to 0, f prime is equal to 0, we also need to compute where f prime of x doesn't exist. And the way a function can achieve this is by having a division by 0 error, meaning the denominator has to equal to 0. So if we set this equal to 0, and then we divide this by 2, divide this by 2, we're going to get that 0 equals to x plus 1. Power of 3 over 2. Now to cancel out this power right here, we're going to raise both sides to the power of the reciprocal of this. So we're going to get that 0 to the power of 2 over 3 is equal to x plus 1 power of 3 over 2 to the power of 2 over 3. And we're going to get that 0 equals to x plus 1, meaning x equals minus 1. And as we know, this right here is the asymptote. So we have got two critical values. Here is the first one, and here is the second one. Now we can go ahead and draw our number line. And I'm going to draw the number line from -1 to infinity because, again, the domain only includes from -1 and onwards. And we know that the other 0 that we got was x equals 0, which is somewhere here. So if we take a value in this interval from 0 to infinity and plug it into our function, which is right here, we are going to get a positive value because there are going to be no negative signs. However, if we were to take a negative value within this interval and plug it into this function right here, we're going to get a negative value here because this value right here would be negative, this value would be positive, and this value right here would be positive. So we would get negative times a positive, which is a negative, and then divided by a positive, which is a negative. So in this interval, our function is going to be decreasing. So here you go, we've computed our intervals of increase and decrease, and it's time to move on to the next step. So step number 6 tells us to find the max and mins of the function by setting the derivative equal to 0 or does not exist. And to find the intervals, we've already kind of done that. So we know that our points, our critical values, are x equals -1 and x equals 0. All that's left to do is to figure out what these values are. Now we know x equals -1 is an asymptote because of the domain and range and because of the limit test that we've done. And also we know that this right here is going to be a local minimum because the interval changes from negative to positive. So we are going to have something like negative, and then we're going to go up to positive, meaning we're going to have a local minimum. And now we know actually what the value of x equals 0 is. The point is going to be 0, 0. And we've computed this already with our x and y intercept. Now that we've computed our local min and max, it's time to move on to step number 7. Step number 7 tells us to find the concavity by computing f double prime. So let's go ahead and do that. So we've had f of prime, which was equal to this function up here. Now we need to find f double prime of this function, meaning we need to take the derivative of x times 3x plus 4 over x times x plus 1 to the power of 3 over 2. So now we can go ahead, and right before I take the derivative, I'm actually going to simplify the numerator of this function. Okay, so now let's start, and we can do it in a similar fashion by using quotient rule. So there we go, we've applied quotient rule, and now we are going to simplify. So now if we notice, we have common factors in the numerator, and I'm going to go ahead and factor them out. Made a little mistake here, I just caught it. This should be to the power of a half, and this should be to the power of a half. But I'm going to stay on the same step. I'm just going to factor out the common factors. So now I'm going to cross out the common factors in the numerator and the denominator. And now I'm just going to go ahead and simplify this function. So there we go. We have computed our second derivative, which is right here. And again, we're going to set f double prime at x equal to 0 to find our intervals. So let's go ahead and do that right now. Again, we can cross multiply this upwards, and we're going to be left with 0 equals to 3x squared plus 8x plus 8. Now this right here actually has no zeros, or no real zeros, because we know that the discriminant, b squared minus 4ac, if this is less than 0, then we're not going to have any real zeros, we're just going to have imaginary ones. And we can see that this is the b value, this is the a value, this is the C value. So if we plug this in, we're going to get minus 32. And that's less than 0, so we're not going to have any real zeros. So that means the number line for concavity would go something like this, from -1 to infinity, and we're not going to have any breakpoints anywhere here because we're not going to have any zeros. And so let's compute the concavity on the entire interval. If you were to take any value, let's take 0 actually, because it's a pretty easy value to plug in, and then compute what sign we're going to get. So if we were to take 0 and plug it into our function right here, we are going to get a positive value, because this term right here would be 0, this term right here would be 0, this would be a positive term, and then the bottom would be a positive term as well. So we're going to get a positive second derivative on this entire interval, meaning that we're going to be concave up on the entire interval of the function. Lastly, we're on step number 8, which is to put everything together. So here it is. I've drawn a axis, and basically we're going to start from step 1 and put everything together. So if we go back up to step 1, we see that we have a domain that is x is greater than -1. So I'm going to go ahead and mark x is -1 on our axis. Let's put it somewhere right here. Now we're going to go up to step number 2 and figure out what we had there. In this case, we had the x and y intercept, and in both cases they were 0, 0. So let's go ahead and plot that point on our axis. Back up to step number 3, we see that we don't have a symmetrical function, so there's nothing for this one to plot. It's just like a side note to us that we're just going to keep in the back of our mind. And if we draw something that looks symmetrical, we know it's going to be wrong. So let's just keep that in the back of our mind. On to step number 4, we can see that right here we figured out that the limit as x approaches infinity is going to be infinity. So we're going to jot that down. And also we figured out that the function as it approaches -1 from the right approaches infinity. So we have an asymptote there. I'm going to basically plot these two on the graph. So firstly, we know that we have an asymptote here. So we're going to mark it by this dotted line. And we also know that the function approaches infinity as we approach this asymptote. So I'm going to draw this little line right here with an arrow signifying that as we approach this from the right, we're going to approach infinity. And we also know that the function is going to go upwards to infinity here as well as x goes to infinity. So I'm going to draw this arrow right here telling us that we're going to be going to infinity as x goes to infinity. So that was step number 4. Now for step number 5, we have figured out the intervals of increase and decrease as well as some critical values. So looking at over here, we know that we have on -1 to 0, this interval right here, we are decreasing, meaning our function is going downwards. And from 0 to infinity, which is this interval right here, we are going upwards, so we're increasing. And that kind of makes sense from the function, but I'm going to go ahead and quickly plot that. So over here, we're going to be something like this, decreasing, but over here, we're going to be like increasing. So I'm just going to go ahead and leave this like that. And by the way, we can already see what the function is going to start looking like. However, I'm just going to go ahead and go through the other steps too. In step number 6, we figured out that x minus 1 is an asymptote and x equals 0 is a local minimum. So at the local minimum, we're going to draw something like this. And now for the final step, number 7, we have figured out the second derivative as well as points of inflection. However, there were none in this case. And we also figured out the concavity, saying that it was concave up on the entire interval of this function. So as we can see, it's already concave up on the entire interval, like it's opening upwards. So we're ready. We've plotted everything that we know about this function, and all we're ready to do is just connect these lines. So there we go, we've plotted the function. It looks kind of choppy because we freehanded it, but it's supposed to look something like this right here. So obviously over here it's kind of choppy and stuff, but we get the gist of it. We understand how the function is going now, and we have successfully sketched this function by following each of these 8 steps. So that's it for this video. Hopefully you guys have learned how to sketch a curve now by following the set of 8 steps. If the videos helped you out at all, please like and comment as to what it helped you out with. Like usual, if you're new to the channel, Please like, comment, and subscribe. It's greatly appreciated. And yeah, I'll catch you guys in another video.